Let's go. Number 10. The death of the universal now. Right now, on a passing train, two lightning bolts strike the platform at opposite ends. From the platform, they hit simultaneously. From the moving train, one hits first. Both observers measure correctly. There is no fact of the matter about which one really happened first, and this isn't philosophy. This is a corollary of every experiment ever done on light. In 1905, a 26-year-old patent clerk in Bern was trying to reconcile a nagging inconsistency between Maxwell's equations for electromagnetism and Newton's laws of motion. It wasn't glamorous work. He wasn't hunting metaphysics. He just wanted the math to stop contradicting itself. Under Newton, time is a river. It flows at one universal rate for everyone, everywhere. Your now, and the now of a person on Mars, the same instant. The clock on a moving train and the clock on the platform tick together. That was the rule for 218 years. The clerk found that if the speed of light is constant for all observers, which experiments had already confirmed, then the universal now cannot exist. Two events simultaneous for one person can happen in a definite order for another. There is no shared present. Albert Einstein published this result in Annalen der Physik in June 1905, in a paper titled On the Electrodynamics of Moving Bodies. The train and platform thought experiment, two lightning strikes appearing simultaneous to a stationary observer and sequential to a moving one, is the standard demonstration. Every physics department on Earth teaches it. Every satellite depends on it. Newton's absolute time was defended for decades. Hendrik Lorentz tried to save it by proposing that clocks physically contract inside an invisible ether. The math worked, but no ether was ever found. Henri Poincaré proposed observer-dependent time as a mathematical convenience, then backed away from the metaphysics. Ernst Mach dismissed the whole framework as philosophical excess. Every rescue attempt required inventing an undetectable medium or denying the experiments outright. None survived. The moment you are reading this word does not exist for someone on a passing asteroid. Their now contains a version of you already finished with this sentence, or not yet started. Your present is local. It ends at the edge of your body. So which one of you is right about what is happening right now? And if the answer is neither, what exactly is now a name for? The problem gets deeper when you look at what your brain is actually doing. Number 9. The 2-second delay you live inside. In 1890, Harvard psychologist William James was trying to describe what conscious experience actually feels like from the inside. He was writing a textbook. He noticed a problem no one had named. The present moment of experience isn't a point in time. It has thickness. It has duration. The physics of time treats now as an infinitesimal slice, a knife edge between past and future, with no width at all. Every equation of motion assumes this. Your intuition assumes this. The word instant means exactly that. No duration. James measured it and found the felt present is roughly 2 to 3 seconds long. Your brain stitches together sound, vision, touch, and memory arriving at different speeds, then serves you a smooth loop and calls it now. The knife edge is a lie your neurons tell. The phenomenon is called the specious present, coined in James's 1890 work The Principles of Psychology. Modern neuroscience has confirmed and refined it. Work by Ernst Poppel at Ludwig Maximilian University in Munich, summarized in a 1997 review in Trends in Cognitive Sciences, pinned the integration window between 2 and 3 seconds. Visual signals reach your cortex in about 100 milliseconds. Auditory signals arrive in 20 to 50. Your brain waits, aligns them, then presents now. Neuroscientists have tried to locate a single now clock inside the brain. None exists. The suprachiasmatic nucleus tracks circadian rhythm, not the felt present. The cerebellum handles millisecond motor timing, not conscious experience. The thalamus was proposed as a binding hub, but binding experiments show no unified pulse. Others propose the illusion emerges from cortical oscillations, but the frequencies vary wildly between subjects experiencing the same now. Every candidate mechanism produces the illusion. None explains it. The word you just read reached your eyes about a third of a second in the past. The feeling that you are experiencing it right now was assembled by a brain that runs perpetually behind the world. You have never once experienced the present. If the now you live in is a construction, who or what is running the construction, and why does it feel so seamless? If your present is manufactured, physics has a stranger question. Why does time move forward at all? Number 8. The arrow that points nowhere fundamental. In the 1870s, Austrian physicist Ludwig Boltzmann was trying to derive the second law of thermodynamics from Newton's mechanics. Simple ambition. He wanted to explain why hot coffee cools, why ice melts, why eggs break but not unbreak. Every underlying equation was time-symmetric. The behavior wasn't. Every fundamental law of physics, Newton's, Maxwell's, Einstein's, Schrödinger's, runs the same forward and backward. Play a film of two billiard balls colliding in reverse, and no equation is violated. The math has no preferred direction. Boltzmann proved the arrow of time isn't in the equations at all. It emerges only from a statistical fact. There are vastly more disordered arrangements of matter than ordered ones. Time flows forward, because entropy statistically increases. That's it. Boltzmann published his H-theorem in the Sitzungsberichte der Akademie der Wissenschaften in 1872 and formalized the statistical foundation in 1877. The probability that a randomly chosen microstate of a modest gas volume is more ordered than the previous one is astronomically small. A number so tiny it's written with roughly 10 to the 23rd power zeros behind the decimal. That's not a small number, that's an unwritable one. But it isn't zero. Physicists have tried to derive a true arrow from deeper principles. Roger Penrose at Oxford proposed the low-entropy Big Bang as the source, but this pushes the mystery back one step. Why was the initial condition so ordered? Sean Carroll at Caltech has argued the arrow emerges from cosmological expansion, but the math works either direction. Julian Barber has argued time itself is illusory, and only relative configurations exist, a beautiful theory that no experiment can distinguish. Every proposal replaces one mystery with another. The reason your coffee cools, your body ages, and your memories only run one way is not a law of nature. It's a statistical accident inherited from the first moments after the Big Bang. If those initial conditions had been average, you would remember tomorrow. So if the universe had rolled slightly different dice 13.8 billion years ago, would you be reading this sentence backwards? The situation becomes stranger when you ask what the future actually is. Number 7. The universe where your death already exists. In the early 1900s, Hermann Minkowski was trying to give Einstein's special relativity a clean geometric interpretation. He was a mathematician, not a mystic. He wanted the equations to sit in a proper four-dimensional space. What fell out of that geometry unsettled him. Common sense says the past is fixed, the present is happening, and the future doesn't exist yet. Only now is real. The future is a set of possibilities waiting to be selected. This is called presentism, and every human intuition supports it. Minkowski's four-dimensional spacetime treats every moment, every past instant, and every future one as equally real coordinates in a static block. Under relativity's math, now is just a label observers assign to slices of a structure that already exists in full. The view is called the block universe, or eternalism, formalized in Minkowski's 1908 address to the German Association of Natural Scientists and Physicians in Cologne. It sits inside every solution of Einstein's field equations. Kurt Gödel, in a 1949 paper in Reviews of Modern Physics, argued that relativity is logically incompatible with an objective flow of time. The math permits closed time-like curves. The math treats the future as extant. Attempts to rescue presentism have all struggled. The growing block model, where the past is real, the future isn't, and the present adds new slices, was proposed by C.D. Broad in his 1923 book Scientific Thought and revived by Michael Tooley in his 1997 work Time, Tense, and Causation. It requires a preferred now slice, which relativity explicitly forbids. Presentist philosophers like Dean Zimmerman at Rutgers have tried to reconcile it with relativity through preferred foliations, but no experiment has ever detected one. Every attempt to smuggle flow back into physics adds structure the equations don't need. If eternalism is correct, the moment of your death is already sitting in the block. Your birth is still happening. Every kiss, every argument, every last breath, all of them exist right now at their own coordinates. You are not moving through time. You are a shape in it. If the future is already there, what exactly is the sensation of choosing? And is it choosing anything at all? This is the point where most people ask for evidence, and physics has some, running invisibly overhead. Number 6. The 38 microseconds that bend your day. In the 1970s, the U.S. Department of Defense was trying to build a satellite navigation system precise enough to guide weapons, ships, and later civilian phones. Engineers ran into a problem they hadn't planned for. The clocks aboard the satellites didn't match the clocks on the ground, not by drift, by physics. Under classical Newtonian mechanics, a clock is a clock. It ticks the same in orbit or on the ground. Any variation should be mechanical error, thermal drift, vibration, quartz aging, fixable, predictable, small. The satellite clocks ran 38 microseconds fast every single day, and the deviation matched Einstein's equations to the decimal. Special relativity slowed them by 7 microseconds due to orbital velocity. General relativity sped them up by 45 microseconds due to weaker gravity at altitude. Net gain, 38. Neil Ashby of the University of Colorado at Boulder documented the correction requirements in detail in a 2003 paper in Living Reviews in Relativity titled Relativity in the Global Positioning System. Each of the 24 GPS satellites orbits at roughly 20,200 kilometers, moving at 3.87 kilometers per second. Without the relativistic correction, positional error would accumulate at about 10 kilometers per day. Your phone would guide you into a lake by lunchtime. Engineers initially assumed the effect was a design flaw. They rebuilt clocks. Same result. They suspected radiation damage in orbit. The effect was constant, not degrading. Some early skeptics inside the program refused to apply the relativistic correction, calling it a theoretical overreach. The satellites went out of sync within hours. The correction was permanent from launch onward. There is no engineering fix, only Einstein's math works. Every direction to a coffee shop, every rideshare pickup, every plane landing you have ever been on works because time literally moves at different rates at your feet than at your head. The proof is not in a lab, it's in your pocket. So if time bends this much this easily, how much of what you call duration is even yours? That was the reassuring item. The next one dismantles the past itself. Number 5. The past that waits for you to check. In 1985, physicist Anthony Leggett at the University of Illinois was trying to figure out whether quantum mechanics survives at large scales, or whether classical behavior takes over once systems get big enough. He and Anupam Garg proposed a mathematical test, an inequality that any object with a definite history should obey. Common sense says an object has a definite state at every moment, whether anyone measures it or not. The moon is there when nobody looks. A coin is heads or tails inside the closed hand. The past is fixed. Measurement reveals a state. It does not create one. This is called macro-realism. The inequality has been tested, repeatedly, in superconducting circuits, in nuclear spins, in photons, and it fails. Quantum systems violate it. Their past is not fixed until you measure. The measurement doesn't reveal history. It selects one. Leggett and Garg published their inequality in Physical Review Letters in 1985 in a paper titled Quantum Mechanics versus Macroscopic Realism. Experimental violations followed for 2 decades. Agustin Palacios Laloy and collaborators at CEA Saclay demonstrated a clean violation in a 2010 paper in Nature Physics using a superconducting qubit. Later tests using nitrogen vacancy centers in diamond and photonic systems at multiple institutions have repeated the violation. The effect exceeds the classical bound by several standard deviations. It is not statistical noise. It is structural. Physicists have tried to preserve a fixed past. The clumsiness loophole argued that measurements themselves were disturbing the system, closed by non-invasive measurement protocols. The decoherence explanation argued environmental interaction locks in a definite state, but the violations persist even in isolated systems. Hidden variable theories, in the tradition of David Bohm, propose deterministic underlying variables, but these require either faster-than-light influences or backward-in-time causation. Each rescue costs something worse than the thing it saves. The atoms in your body have quantum degrees of freedom. Their history is not fully determined until interaction forces the issue. You are made of stuff whose past is negotiable. Something in you is still deciding what already happened. If the past isn't fixed until it's checked, who or what does the checking, and when did it get around to you? The past becomes even less stable near gravity strong enough to swallow light. Number 4. Where forward stops meaning forward. In 1916, weeks after Einstein published General Relativity, a German physicist named Karl Schwarzschild was serving on the Russian front. He solved Einstein's field equations for a spherical non-rotating mass while working in the trenches. He mailed the solution back to Berlin. He died of illness months later. His solution described what we now call a black hole. In normal space, time is time and space is space. You can walk backward through the room, but you cannot walk backward through Tuesday. The 3 space coordinates are freely traversable. The time coordinate points one way. This distinction holds everywhere on Earth, in every laboratory ever built. Inside the Schwarzschild radius of a black hole, the equations flip. The coordinate that was pointing through space now points through time. The coordinate that was time behaves like space. Falling toward the singularity becomes as unavoidable as your walk into next Tuesday. The Schwarzschild solution was published in the Sitzungsberichte der Königlich Preußischen Akademie der Wissenschaften zu Berlin in 1916. The coordinate swap occurs at the event horizon, which sits at a radius of about 3 km for a stellar mass black hole and roughly 12 million km for Sagittarius A*, the black hole at the center of the Milky Way, whose mass has been measured at about 4.15 million times that of the Sun. Physicists initially thought the coordinate flip was a mathematical artifact, an issue with the choice of variables, not physical reality. But in 1960, Martin Kruskal at Princeton demonstrated with a new coordinate system that the horizon is real geometry, not bookkeeping. Others hoped quantum gravity would soften the effect. It doesn't. Stephen Hawking's own late work on the black hole information paradox depended on the coordinate swap being physically real. No modern theory removes it. The thing you call the future, the direction you cannot help moving toward, is not a universal property. It's a local one. Cross a specific radius and future becomes a location. You wouldn't fall toward the singularity. You would age toward it. If time and space can trade places under enough gravity, what were they ever, really, apart from a label your position gives them? Not every argument against time comes from physics. Some come from a philosopher who beat physics to the answer by decades. Number 3. The 1908 proof that nothing has yet refuted. In 1908, a Cambridge philosopher named John Ellis McTaggart was working on a book about the nature of reality. He wasn't debating physicists. He was pursuing a metaphysical argument in the British idealist tradition. Along the way, he tried to state clearly what time actually is. He concluded it isn't anything. Time, most people would say, has 2 features. Events are ordered, earlier and later, and events change status. Future events become present, then past. Any coherent description of time needs both. This seems obvious to the point of banal. McTaggart proved the second feature is logically incoherent. Every event, he argued, must be past, present, and future, which are contradictory properties. Trying to fix this by saying at different times produces infinite regress. Time as flow cannot be logically stated without contradiction. McTaggart's argument appeared in a paper titled The Unreality of Time in the philosophy journal Mind in October 1908. He labeled the 2 aspects of time the A series, past, present, future, and the B series, earlier and later. He showed the A series is contradictory. He then argued the B series alone cannot capture change. If neither series can describe what time is supposed to be, time itself is unreal. Philosophers have spent 118 years trying to refute him. C.D. Broad at Cambridge proposed the growing block model to preserve the A series. Critics showed it still smuggles in an unexplained now. D.H. Mellor at Cambridge argued in his 1981 book Real Time that the B series is sufficient and change is illusion, a position many physicists quietly hold, but it concedes McTaggart's core point. L. Nathan Oaklander has tried to reformulate the A series to avoid contradiction. No formulation has survived scrutiny without either denying flow or invoking undefined primitives. The thing you feel most certainly, that time passes, that yesterday is gone, that tomorrow is coming, cannot be stated in a form that survives basic logic. Your most immediate experience of reality may be logically impossible to describe accurately. If passage cannot be logically described, is what you are experiencing right now really passage, or something else you have only ever called by that name. Physics has largely stopped ignoring McTaggart. One equation in particular takes his conclusion seriously. Number 2. The equation of everything with no time in it. In 1965, physicist John Wheeler at Princeton was trying to unite general relativity with quantum mechanics, the two most successful theories in physics, which disagree on almost everything. He met with Bryce DeWitt at the University of North Carolina during a stopover at Raleigh-Durham Airport. Between flights, they sketched what a quantum theory of the whole universe would look like. Every equation in quantum mechanics contains time. Schrödinger's equation describes how quantum states evolve as time passes. Every prediction physics makes involves a time coordinate, how a system changes as t advances. Without t, quantum mechanics simply doesn't function. When Wheeler and DeWitt wrote down the correct equation for a quantum universe, the time variable dropped out. Not by accident, by necessity. The equation describes a wave function of the entire cosmos, and it is a static, timeless expression. Nothing evolves, nothing ticks. The Wheeler-DeWitt equation was formalized in DeWitt's 1967 paper in Physical Review, titled Quantum Theory of Gravity, I, the Canonical Theory. Written as HPCI=0, it states that the Hamiltonian of the universe acting on the universe's wave function equals 0, meaning the wave function does not change. The most fundamental equation ever proposed for the cosmos has no time term, anywhere. This is called the problem of time, and physicists have proposed rescues for 59 years. Don Page and William Wooters proposed in a 1983 paper in Physical Review D that time emerges from correlations between subsystems. Elegant, but no experiment confirms it. Carlo Rovelli at Aix-Marseille University proposed thermal time, that time emerges statistically from thermodynamics, but the derivation only works in specific systems. Julian Barber embraces the timelessness entirely and argues we live in an eternal now, a philosophical position with no predictive power. No proposal is agreed upon. If the equation is correct, and 59 years of testing haven't broken it, the universe at its deepest level is not evolving. It is not ticking forward. It just is. And whatever you feel happening right now is a story your local scale tells you. If the universe itself does not experience time, where, exactly, is your sense of time coming from? Which brings us to the most honest admission in physics, one every serious theorist makes when the microphones are off. Number 1. The problem physics cannot solve. For the past 4 decades, every major program attempting a theory of quantum gravity, string theory, loop quantum gravity, causal set theory, asymptotic safety, has been trying to unify general relativity's smooth spacetime with quantum mechanics' discrete probabilities. Each program started with different assumptions. Each ran into the same wall. A working theory of quantum gravity should tell us what spacetime is really made of at the smallest scales, and how the flowing time we experience emerges from whatever is more fundamental. It should recover our world at ordinary energies while explaining what happens inside a black hole or at the Big Bang. No candidate theory has recovered time. Every deep formulation ends up timeless, mirroring Wheeler-DeWitt, and no derivation cleanly explains why we experience seconds passing. The universe's fundamental description does not need time. Ours does. Nobody knows how the second thing comes from the first. The problem of time is discussed openly in the field. Carol Kusher, at the University of Utah, cataloged 10 distinct proposed solutions in a review published in the Proceedings of the 4th Canadian Conference on General Relativity and Relativistic Astrophysics in 1992, and concluded none worked. Chris Isham at Imperial College London wrote a companion review in 1993, concluding the same. 3 decades on, no solution has achieved consensus. Recent reviews in classical and quantum gravity restate the problem as open. Every proposed way out has failed on its own terms. Emergent time from entanglement, championed by Mark van Ramsdonk at the University of British Columbia, works in toy models but not full theories. The Page-Wooters mechanism recovers time from a subsystem clock but leaves the total universe timeless. Loop quantum gravity gives a discrete spectrum for spatial areas, but no operator for duration. String theory's standard formulations assume time in advance, begging the question. Causal set theory builds time inatomically, at the cost of Lorentz invariance, which experiments demand. No approach walks the whole line. The scientists most qualified to tell you what time is have admitted in print that they don't know. Your body runs on the flow of time. Your grief runs on it. Your hope runs on it. The physics of it is a placeholder. The equations run without it. If the universe doesn't need time to run, why do you? Every anomaly on this list sits inside physics' most tested equations and is admitted openly in mainstream journals. The universe isn't confused about time. It doesn't seem to have one. You are the thing carrying the sensation of flow, of before and after, of now. The equations run fine without it. Which raises the question this whole video was really about. If time isn't real out there, what is the thing you are actually experiencing in here? If you want to see more videos like this, click the video on screen now.